In this assignment, we practice more velocity and acceleration problems. So we're doing straight line motion or rectilinear, and we've got a particle moving along a straight line with position function s. And our velocity function, then, we know is the derivative of the position function. So when we write s prime, we know that we're differentiating with respect to the same independent variable. So we're differentiating with respect to t, so we don't need the chain rules that we did when we did implicit. This would be explicit differentiation. So we just do the power rule here to find our velocity function. Our next question says, can we use that function and find the velocity at time 3? So you would want to just do this calculation. So it looks like we'd have a 27 minus a 72 plus a 36. So I think we'll come up with a negative 9 feet per second. Make sure always that you have included units in your answer. When is the particle at rest? Well, that would be when its velocity is equal to 0. So let's take our velocity function and set v of t equal to 0. And I think we would want to factor a 3 right away. And if this is not in a calculator section, then expect it to be factorable. If the numbers aren't so nice, then you would have your calculator to help. So I guess we want a 6 and a 2 to add to 8. So at time equals 2 and time equals 6. So we should justify our answer. The particle is at rest at t equals 2 seconds. We can just write s for seconds. And t equals 6 seconds, since v of t is equal to 0. So stay in good habit of justifying our answers here. When is the particle moving in the positive direction? That would be the same as asking you when is the particle moving to the right. That would be equivalent. And that would be when the velocity is positive. So our critical numbers were where our first derivative was equal to 0. So we want to test the intervals around our critical numbers. And remember, at the start of the problem it said this was when time is greater than or equal to 0. So we could test our intervals and find out what we know about velocity. And the test that you want to do, use this factored form. Quicker to use the factored form. So on our interval from 0 to 2, our first critical number, if you think about putting a number like 1 in for time, you can see we'd have a positive 3 times a negative number times a negative number. So the product of two negatives and a positive velocity would be positive. And we expect it to alternate. But until you're used to that, we can test it out. If we tried a number like time equals 4, you can see that this t minus 2 parenthesis changes to positive. So we'd have a positive 3 times a negative times a positive. So only one negative. So our velocity would change to be negative. And then once we go past 6, and that would be true to infinity theoretically. So if we take a large number for t, all 3 factors are positive. So you don't have to spend too much time testing these intervals once you get used to the idea of how they're going to alternate at single roots. At double roots, that's not true. The sign is not going to change because it would be like 2 factors changing signs at the same time, and the 2 negatives would cancel each other out. So in any case, here our question is, when was it moving to the right? So we would say over the intervals from 0 to 2 and 6 to, I guess, infinity. This is that same problem I had in my worksheet in class where I didn't give you this upper limit. So technically you could say to infinity here. If you notice that we're going to use the interval 8, you could just say 6 to 8 here. But either way, since v of t is greater than 0. So again, that justifies that the object is moving to the right when its velocity is positive. All right, our total distance traveled then, and then we're going to, whoops, sorry, scrolled kind of funny there. Our total distance, and then we're going to make our diagram so we can think about this if we can find the position at the endpoints and at the critical numbers. So let's find out where it is using our position function. And notice here we've got an upper bound of 8 seconds, so that's our endpoint at the other end. So you want to do some calculating, and I've already done that. You can check this out and make sure you agree. I have 0, positive 32, back to 0, back to 32. So the total distance traveled, it traveled 32 feet in this interval, and then it traveled 32 feet backwards, and then it traveled 32 feet forward again. So the total distance looks like it would be 96 feet. And again, you weren't asked this question, but it's interesting to notice here that the net distance is only 32. So make sure that you're not mixing up those terms. Net distance or displacement might come up in some other types of problems. So here we were only interested in total distance. All right, so we can use all of that information then to make our snake-like graph here. We know the object started at 0, it went over to 32, we'll put it there, it came back to 0, and then it went back to 32. So just set up a diagram where it can snake forward and backwards, and then just give us the key information here. At time 0, the position was 0. At time 2, our position was 32. At time 6, the position was back to 0. And at time 8 seconds, our position was back to 32. So it's a little confusing. Remember that this s is not seconds, it is the s of t function, it's the position. And then we should put some arrows to show the path. And remember the object is actually staying on the x-axis, so that snake-like graph is just to help us see its total path. All right, and acceleration. So remember that the second derivative of the position, in other words, the first derivative of velocity, is the acceleration function. So take your velocity function and use your power rule, and we'll come up with 6t minus 24. And then this question, it said to find the acceleration function at all times. And then let's specifically find out what its acceleration is at 3 seconds. Mostly a question here to make sure you label the units correctly. So 18 minus 24, negative 6, and then that would be in the same units of your velocity, feet per second, but per second again. So you can leave it that way, feet per second, and of course it's acceptable to put feet per second squared. All right, that next derivative, if you do the derivative of the acceleration function, that's one of our favorite calculus jokes here. Don't be a third derivative. Remember that the derivative of acceleration that would be the third derivative of the position function, t, s of t, and that is called the jerk function or the jolt function, but of course this joke is referring to it being called the jerk function. And you can think why. If acceleration is changing rapidly, you're going to have kind of a jerky ride. All right, so don't be a jerk. In number 2, now we want to use graphs to think about. So here we have graphs of velocity functions. So we want to think about when a particle is speeding up and when is it slowing down. Now be very careful when you see these problems, because our temptation is always to think that an object is only speeding up when its velocity is rising in the positive direction. But remember, that's not true. So if you're backing a car up out of the driveway, you know that you could also be speeding up your car. So acceleration has a change of distance. It has direction. So acceleration is not just in the positive direction. So our best way of saying this is an object is speeding up. Let's actually come up with a nice calculus way of doing this. Speeding up when acceleration and velocity have the same sign. They're not working against each other. So the analogy I've used for that in class previously when we've done these problems, if you were running down the hallway, if I gave you a shove on your back, you would move faster in the same direction you were going. So I would be accelerating you. I would be speeding you up because I pushed you in the same direction that you were going. Think what would happen if you were running towards room 109. I stepped out and I put my hand up against your chest. I don't know if I would be able to stop you, but I certainly would slow you down. So that would be because the acceleration would be contrary to the velocity. So when acceleration and velocity are both positive, you're moving faster in the forward direction. When acceleration and velocity are both negative, you're moving faster in the negative direction. So we better think about velocity here. So we know here, and this seems kind of obvious, we know in this interval that velocity is positive, and in this interval velocity is negative. But now let's think about acceleration. So acceleration comes from the slopes. Acceleration is the derivative of velocity. So the acceleration, velocity is rising, so acceleration is positive in this region, and then the velocity is decreasing the rest of the way. So acceleration here would be negative. So we want to look, that would be all the way to the end of the graph there. So we want to look for where is acceleration and velocity in the same direction. So I haven't really left myself any room for an answer here. So I'll say speeding up right here. So I notice that velocity and acceleration are both positive in this section of the graph. So velocity and acceleration are working together there. So speeding up on the interval from 0 to 1. And velocity and acceleration are both negative in this region of the graph. So from, and now I've just covered that up, I guess our graph goes from just 2 to 3. And on 2 to 3, and how do you justify that? You would say since acceleration and velocity have the same sign. So remember, they can both be positive or they can both be negative. So that's actually my final answer. Get rid of some of these circles here and do a better job. That's what you want to write on your paper. All right, so let's take a look at B, see if you've got the idea. You might want to pause and try this one first and then start the video again. So we're looking for where do velocity and acceleration have the same sign. So I notice that velocity is positive from 0 to 3. So again, I'm writing the obvious here. You can just think this through. Velocity is positive, and then from 3 to 4, velocity is negative. And acceleration is quite a bit different. Acceleration comes from the slopes. So notice that our velocity has a negative slope from 0 to 1. So here the acceleration function will be negative. And then we're rising from 1 to 2, so acceleration would be positive. And then our slopes of our velocity function are negative. So the slopes of velocity tell you about acceleration. So the slopes of the velocity there are negative. All right, so do we have any place where it matches? Well, I see one interval. Let me try another color here. Do you see one interval here where they're both positive? Acceleration and velocity are both positive. And then we have one more interval over here, it looks like, where velocity and acceleration are both negative. In the other two regions, the acceleration and the velocity have opposite signs. So they're working against each other. Okay, so our answer for this problem would be that the particle is speeding up on the interval from 1 to 2 and on the interval from 3 to 4. And now you could do this, since A of t and V of t have the same sign. All right, so again, make sure you include that justification. All right, now we're going to look at the same idea. However, this time we have only the position functions to go from. So again, do you see all that work that we did with first and second derivatives? Here we're putting it to an applied purpose. So this time we're given the position functions s for two different particles, but our question is the same. When are they speeding up? So we don't care about what direction it's traveling. We care whether the acceleration and the velocity are in the same direction. So we're only given the position, so we've got to think of the first derivative and the second derivative. So let's talk first about velocity. Velocity comes from the slopes of the position function. So here our position is increasing. So here we know that our velocity is positive. And here the slopes up to this point, the slopes of our position are negative. So our first derivative will be negative, and our first derivative of position is velocity. And then the graph is rising again. So from this interval, our velocity would be positive again. All right, now let's switch gears and talk about the second derivative. Well, the second derivative is easily found if you remember that the second derivative involves concavity. So I see an inflection point right here. So this graph, to me, looks concave down from 0 to 2. So this looks like the second derivative, or the acceleration, is less than 0. And then from 2 to 4, it looks concave up to me. So the acceleration is positive. And you may assume when you look at these graphs that the inflection points and the minimums and maximums have been located at points that are easy to name. Okay, so where are we working together? Where are acceleration and velocity having the same sign? It looks like in this region, acceleration and velocity are both negatives. And in this region, acceleration and velocity are both positives. So the object is speeding up on two different intervals, from 1 to 2 and 3 to 4, where acceleration and velocity have the same sign. All right, so again, if you're not trying these on your own, stop the video here for our position. It is decreasing all the way up to this point. So we know in this section of the graph that our velocity is negative. Velocity is the slopes of the position function, and then the slopes are positive, so our velocity is positive here from 3 to 4. And then let's look at concavity to come up with what we know about our second derivative, our acceleration. And I think it looks concave up, so I suspect we were thinking this was an inflection point. So that's what I'm looking for where concavity changes, are inflection points. So I would say it looks concave up to me, and then it looks concave down just till there. And then that parabola looking shape looks concave up to me. So I would say the concave up section here, acceleration is positive. From 1 to 2, I say it is concave down, so acceleration negative. And then from 2 to 4, concave up again, so acceleration positive. So where do we have speeding up when acceleration and velocity have the same sign? So from 1 to 2, they appear to both be negative, and from 3 to 4, they appear to both be positive. So some simple practice here, but looking at the graph. So take your time when you're doing these to make sure that you don't make a mistake on such a problem that could be so easy. It is speeding, not the word upon, that should be up on, speeding up on the interval from 1 to 2 and 3 to 4. Same reason, because acceleration and velocity have the same sign. So remember that you can be speeding up even when you are going backwards. Okay, vertical motion problem. A ball is thrown vertically upward with a velocity of 80 feet, and its height after t seconds is given as this function. So you'll get very used to these parabolas. Remember, the negative 16 is due to acceleration due to gravity. So you did this problem many times in Algebra 2, and remember, for parabolas in algebra, don't do this anymore, but in algebra you know the formula for the x-coordinate of the vertex. So in this case it's not an x-coordinate, it's a t-coordinate, but the opposite of b over 2a gave you your first coordinate of the vertex. And that's still true for all parabolas, so you can certainly go back to do that to check your answer. But this would get you 0 points on a calculus exam. So to find our maximum height, we want to say, well, it reaches its maximum height when its velocity is equal to 0. So s prime is our velocity function, and that would be 80 minus 32t. So it reaches its maximum height when the velocity is equal to 0. So let's find out when that is. And you don't have to show each of these steps. So we want to divide by 32, and we can divide that, by 16, and get 5/2 seconds. And that's when it reaches the maximum height. But the question says, what is the maximum height? So don't forget, we're not finished. So now find the height. S is the position function, so find s at 5/2 second. So we want to do 80 times 5/2 minus 16 times 5/2 squared would be 25/4. So this is not meant to be difficult. So if this was in a non-calculator section, you could still do this. 40 times 5, 200, minus 40 times 4 times 25, 100. So it looks like we are at a maximum height of 100 feet at 2.5 seconds. One more question to go here then. What is the velocity when the ball is 96 feet above its starting height? Well, we have to go to our s function here and say, when is the height 96? So first we have to find out what time we're talking about here. So let's use our position function and find out when our height is equal to 96. And again, this would be made to be a factorable problem. So let's see, maybe we might want to move things to that side, have them be positive for our first term. So if we factor a 16, now this is an equation, so we could divide the 16 out of both sides. I'll leave it here just as a reminder of what we're doing here, and 6 times 16 is 96. So if this is in a non-calculator section, it would be factorable. So we get time equals 3 or time equals 2. And now be careful here. It says we only need to figure this out on its way up. So the 2 seconds must be on the way up, and the 3 seconds must be when it reaches the same height on the way down. Okay? So we need to do both, I guess, for the second question. So on the way up, we want to find out the velocity of the ball at time 2 seconds. That would be on the way up. So we would have, use your velocity function now, not your position. And we would come up with 16 feet per second on the way up. And on the way down, we would do the velocity at 3 seconds. So 80 minus 32 times 3. So we'll have negative 16 feet per second. So now, I guess we know where the vertex is, of course. The vertex is always symmetrically between those two. So we know the velocity would better turn out to be 0 if you put 2.5 in. And of course, we had already known where the vertex was in the previous part. That should do it.